So good morning, everyone. So you might notice that the title of the talk is slightly different, but the question that I posed in the original title will be answered. I thought this title does more justice because what we think is that reconfigurable computing and all the work that you guys have done and are doing as part of ORCONF platforms and other similar platforms will probably go more mainstream. So my name is Gaurav Kaul, I'm a solutions architect at Intel, which means I actually work with end customers who use our platforms to optimize the codes and so on. So agenda for today's talk is to basically just have an overview of accelerators. I think most of you probably are aware of all this. Again, have a look at FPGA as an accelerator, what that entails. Then we are going to come on to the Xeon FPGA platform. So the first, we're just going to motivate the problem why Intel is going to this route, because a lot of questions, so we'll just try to understand the landscape better. Then we are going to come to the meat of the talk, which is, which is very much a work in progress. All of this is a work in progress, by the way, but hardware and software programming interfaces, how can we best utilize the techniques of HLS, offload sort of paradigms and so on. And then we are going to look at some example applications which you might have come across at ISCA and some of these other conferences like Microsoft did and other people are doing, especially in the field of deep learning and how it can help, how the Xeon FPGA was used. Not in its proposed form, but at least in an accelerator way. I think we all know this. Moore's law is still there, but we have hit a scaling limit on frequency, and this is due to Dennard scaling, which didn't progress, which kind of died out in 2003, 2004, which essentially means that due to leakage current, as opposed to due to leakage losses, as opposed to bandwidth losses when the transistor switches on and off. We really can't go beyond a particular threshold limit. All Intel processors now operate at 0.7 volts, which is pretty much the VDD threshold. Going anything beyond that is not going to completely, it's not going to switch on the transistors on and off. So Dennard scaling, due to this limitation, we have hit a frequency wall. So this is a graph from CPUDB at Stanford, which shows how transistors, clock frequency, power dissipation, performance, and cores have trended over the years, specific for Intel platforms. So you can see that up till 2002, 2003, it was pretty much a linear scaling of frequency, rather exponential scaling of frequency. Exponential scaling of transistors is still somewhat ongoing. But after 2002, 2003, we sort of hit the limitation. And now what is scaling are the number of cores, the ones in the pink, orange, no sorry, in the orange. Because what we have done is we have traded off single thread performance and in fact gone on to multi-thread performance. So keep the frequency as it is, increase the number of cores, somehow find the parallelism in your applications and run it on that multiple number of cores that it provides you. So this is the situation where we are in at the moment, and all Intel processors and other processors, including GPUs, etc., use this paradigm. So every Intel talk has to have a slide on it, Moore's law. The key point here is that earlier the cadence was 2 years, now it's close to 2.5 years as we reach the well, we are already at the 14 nanometer mark and are progressing towards the 10 nanometer mark. So we have a sort of predefined path towards future 10 nanometer and less feature sizes. So what does this entail really is that we are going to have a lot of transistors, and the question is what are we going to do with them in terms of performance, in terms of better performance per watt sort of metric.
Yeah. One of the things in the previous sheet
is
that I got a talk from somebody else who was saying that actually the price of the transistor was going up. Now, in the previous years it was always going down, so there will be a different market trend,
Yeah.
because silicon does not get cheaper.
Yes, absolutely.
Correct or not?
To some extent, that is correct. Obviously, if silicon, so when Intel sets up a fab to do something like 10 nanometer, it's order of billions, and the cost of setting fab also increases. So if 14 nanometer, 22 nanometer costed, say, X billion, the 14 nanometer will cost 2.5x billion. And you are absolutely right. This is why the transistor cost per transistor is increasing. So what is this what is the way to make it economically feasible is to put more of it. And this is why we are trying to increase the ecosystem by going into mobile, by going to IoT, going already in the server and the laptop and so on. So that's the way. This is why it's important for us to scale out to other businesses so that we can actually keep the fabs running as it were because of this condition. So in summary, what we can say that any kind of performance gain on processors from Intel or for anyone is driven by a couple of factors. Moore's law is obviously there, have more chips, etc. Better transistor switching performance, etc. But what we are going to focus in today's talk is new technologies and specifically FPGAs and how it can help us to deliver some extra performance over and top of other three areas that we already work on. So accelerators are going to become more important in future because we have the transistors, we have the estate as it where the die size itself is increasing, right? So we have to find ways to build new accelerators which leverage these transistors in an efficient fashion. Specifically, what we are going to look at is specifically data center. So data center is a very broad term. Generally speaking, I use it not just for high performance computing, but not just for data center as in the Facebooks, the Googles and the Amazons of the world, but also high performance computing. And this is obviously a rapidly growing area. And if you kind of map out the distinct workloads within the data center, they kind of fall on this axis of memory intensive and IO intensive. Obviously, they're CPU intensive as well. So there's probably the third. That's the third dimension over there. So accelerators, what we'd like to do is basically cater to all these three without compromising on a single performance benefit. And the important factor here is that accelerator an accelerator which is co-designed for some of these workloads can help us with at least the memory intensive part or the CPU intensive part. IO intensive is more on the storage, novel storage technologies and so on. But an accelerator can help us with at least the two of axes. And this is what is driving the demand for these accelerators in the data center and in HPC. The problem with the data centers are slightly different as well in the sense that the data center hardware has to be as heterogeneous as possible, as homogeneous as possible. Imagine a warehouse scale computer, which is basically a data center, right? Having how much? So one of Facebook's new data centers, which opened in Utah or some place in Midwest, houses up to 1 million cores, right? So, and is of the length of 5 or 6 football fields. So in order to manage such a large estate of compute, it has to be kept as homogeneous as possible. Failures are expected after every hour. So the more homogeneous you keep it, the more you can control the failure rate and the more easy it's to maintain. So, so there's a competition here. You need to have accelerators, which by nature are special purpose, but you have to keep the data center as homogeneous as possible. So there's the slight tension in these two requirements. We'll come to this later, how Microsoft looked at this problem when they were looking at FPGAs. So there's a whole spectrum of workload acceleration, which again, all of you are familiar with. Have a software library optimized to do a particular task. An example is the math kernel library in the field of high performance computing and scientific computing. Another is DPDK, that stands for Data Plane Development Kit, which is used for packet processing. And then there's storage acceleration. So there are all these different libraries which are optimized for specific domains. So you don't have to kind of code, your own specialized functions. You can leverage the best practices. Then you have discrete accelerators and integrated accelerators. Discrete accelerators are your GPUs, FPGAs attached on a PCIe sort of link, and integrated is like what all of you have in your laptops, basically integrated GPU with the CPU. And then obviously processor instructions. Now the general purpose processor itself is getting specialized. So what now is being incorporated in the processor is things like vector processing. So for example, advanced vector instructions, which is Intel's version of SIMD, single instruction multiple data sort of parallelism, now supports 256-bit wide vector lanes. It supports additional vector functions like scatter, gather, and so on. So processors themselves are getting specialized, but not too specialized. So we rely on accelerators and on software libraries to provide us workload acceleration. And indeed, this entire spectrum, and probably on the extreme side is the ASIC that we have at our disposal, so as to speak, and to some extent we use pretty much most of them in HPC and big data. So let's have a look at some workload acceleration examples. Of course, there's some very media transcoding, cryptography, net compression. These are fairly standard. We'll look at highly parallel implementation. So basically in the realm of high performance computing. So each of these domains have a certain criteria or have a certain characteristic. HPC is characterized by highly parallel, highly threaded, vectorized workloads, lots of floating point operations. Your software has to scale up to plus 100 threads or more if you are supposed to get a good performance. GPUs, for example, or the nice landing Xeon 5, the individual cores are not that are not that powerful, right? So you have multiple of them. So they differ from a standard Xeon, which has a beefier core but less number of them, as opposed to something which has less number of, which has simpler cores and more. So you really need to have that parallelism and scaling that can leverage all those cores, and obviously vectorization as well. And memory bandwidth is sensitive because you have to keep all these cores busy at the same point of time. And this is a big tension, right? Memory bandwidth scales less as opposed to CPU. And if you're suddenly putting 100 plus cores on the CPU, your memory bandwidth per core is certainly not that great, right? So you have to look into that as well. But having said that, HPC is growing at a really breakneck speed. I should have the figure here, but it's doubling every year. Of late, this has sort of has plateaued a bit around 30 petaflop or so. So the Chinese supercomputer Tianhe 1, that has been, I think, the top ranking for the last 2 years, I believe. Well, we will come to know supercomputing, which is next month, which is now usually ranked #1. But this has plateaued, as you can see from the red line over there. The projection is that ultimately by 2022 timeline, some people say there are various versions of it, but people project this line and say that we should hit the exaflop, which is what the holy grail of HPC is at the moment in that timeline. But this is an open question. The top one and the full. So the blue is the cumulative distribution. So this is just an example of a next generation processor that Intel will be sort of launching next year, which is the nice landing Xeon 5. And this is one example of a HPC, a processor which is geared towards high performance computing with on-package high bandwidth memory. Remember what I said about the memory bandwidth with on-package fabric interconnection. So so that you can do MPI-like workloads in a better fashion, and up to 72 cores as well. So this is one example of this. And ultimately, and this is important because we'll touch this topic again when we look at the FPGAs, is that we want to have a general purpose programming model. We don't want a model which forces people to rewrite the code in a completely new language. For example, some of the GPUs have that you have to, and that changes like every 6 months, right? They bring in some next changes. We want the code base to be as stable as possible. Obviously, there will be some enhancement, but people shouldn't be required to rewrite everything from scratch. And the familiar programming model in this case are the MPI, OpenCL, and we would like that the processors leverage that. Because some of the codes that are there, for example, in some of the government labs in the US, they're written in the 60s and the 70s. So, and they can't, for the purpose they are written, they cannot change them, and if they change them, then they need to do some tests which are very troubling. So that's the kind of limitation we have. So hopefully that probably sets the agenda, right, what we have. So in summary, we need to have fairly sort of, not general, but workload-specific accelerator with a very good programming model, which has high floating point operations capability and sensitive and leverages memory bandwidth in a good way. So where does FPGA fit in that landscape? So there can be accelerators, and FPGA is certainly a very configurable architecture, as you know, and that provides it with some flexibility. The key thing to look into is what exactly. So where do we attach the accelerator? So this is important because ultimately, where the accelerator is attached dictates how fast the memory bandwidth can be, how fast you can dispatch workload to the accelerator, how the accelerator can be programmed, and so on. So if the accelerator is on the core itself, the latency, the memory bandwidth that it has, that is quite good, as opposed to when it is on the PCIe card, which is what current day GPUs, FPGAs, etc. are on. You are always offloading it. So I think the memory bandwidth on the 16-lane PCIe, like the peak is of the order of 300 gigabyte per second, which is all right, but this is like single precision floating point. DGEM will pretty much half it, and if you're doing some compute, then half it even more, or probably even more. So the problem is that it suddenly drops. And the other important point is, I didn't cover it in the exaflop slide, is that power is going to be the biggest bottleneck actually in everything. In all compute is constrained by power, from your smartphone to your laptop to the top-end server. Everything now, power has become the first order constraint. So when you are doing a lot of data movement across for an accelerator over something like a PCIe Express, your power dissipation just rapidly increases. So you want to maximize your locality on chip, as it were. And this is why an accelerator on chip or on package is so important and can deliver really, can be a good exaflop or exascale, candidate, because it keeps that power dissipation low due to minimizing the data movement. I think probably all of you have seen this slide. This compares the microprocessors with DSP. It says that something like a DSP or an FPGA or an ASIC is 10x times more power efficient than a general purpose processor, which is the rough figure in terms of energy efficiency, as opposed to ASIC, which is 100x, which is the best part. Then again, what's the programmability of an ASIC? We all know. So the important point is, we would like to have an accelerator which is on core, or at least has a familiar programming model. And for that, what we want is that it should be coherent with the CPU core, so that things like managing the data movement, etc., things like pointer chasing, etc., all that can be done by an average programmer without much issue. Accelerators more mainstream. because it impacts two things. It impacts the data movement, so you can have something like inline. So for example, FPGAs are used inline for packet processing and for some of these use cases in high frequency trading, and also at CERN actually, you want to do inline processing. So you have data coming on through I/O and then you process it online as the data comes along. Or you can do something like shared virtual memory in which the core and the accelerator have access to the same virtual memory and leverage the underlying OS and table mapping, etc. So that eliminates the need of memory buffers and copying and all that overhead associated with that. So that's the coherency model, and this exactly is the point where the Xeon FPGA kind of comes in. So two things: something very close to the core, not as distant as a PCI card, and coherent with the core. Those are the two key criteria that Xeon FPGA tries to fulfill. There are other accelerator models, so for example, FPGA-based accelerator models. So for example, IBM has what is called CAPI, Coherent Accelerator Programmable Interface, CAPI. But what it does is that it attaches the FPGA to a power rate processor on the PCI. It does provide a coherency domain, but remember it's on the PCI. So, yes, you have coherence, but it comes at the attach point of this. So with Xeon FPGA platform, the aim is to have the FPGA on package or on the core as possible. We don't want to have the FPGA on PCI. We don't even want the FPGA on a single. So you have a core here, and then you have FPGA. We don't want that. We want two full socket Xeons, but with FPGAs either on package or on the core itself, on the die itself. So that is the so this is the software development platform that is already shipping today, and it implements a cache coherent FPGA with the Xeon processor. The specs you can see over here. So it's an Ultra StartX 5. It implements the QPI protocol. So QPI is the quick path interconnect. Thank you. Which is the processor-to-processor interconnect that is used by Intel processors. And basically, what it does is that it does MASI-like dielectric coherence between the processors. So if one core changes something in its in the shared cache, the QPI agent that is running on the memory controller, that basically does the invalidation and does the bookkeeping to make sure that the caches are coherent across the cores. And now that coherence domain is being extended on the FPGA itself. So what the software development platform has implemented, it's basically a QPI coherence agent on the FPGA die. So that does all the the QPI file-related works to keep the caches coherent. And the other part of the FPGA is what is known as the AFU, or the accelerator functioning unit, which is basically the accelerator that you have implemented. So it can be some sort of matrix kind of matrix multiply, or matrix operations accelerator, or an image processing accelerator, and so on. So the important point is that the AFU is cache coherent with the processor and on the FPGAs. At the moment, they cannot implement a second level cache, but this is something we are looking into. And it basically participates in the coherency domain. So technically, you can have a FPGA with multiple AFUs, all of them in the coherence domain with the processors, or in multiple sockets. So imagine, so right now, I think it's a single Xeon, and so right now what the SDP has is basically, it's a two-socket system, which has a Xeon on one socket and a Ultra StartX 5 on another, and they are both kept cache coherent by implementing the QPI 5 on the FPGA. But obviously this is just the test platform. In future, what we'll have is you will have the two Xeons on each socket, each having on-package FPGA, and all four of them being cached. So that's the end game that we are looking for. So what are the platform features? FPGA with coherent low latency interconnect, at least to LLC and last level cache. Simplified programming model. It will have a shared virtual memory with the processor. So this will, make possible things like linked list, pointer chasing, and so on. So you don't have to do explicit offloads and data buffer copy and manage that as you do with the GPU and even with current FPGAs using OpenCL. And this really allows us to implement new classes of algorithms. And we'll look at one case study with deep learning and how Microsoft used that for this Bing searches. So this is just some of the details of the RTL that was implemented, but I won't go into this. So the next question is, what is the programming tool here, right? Because that is the key part. We all know, FPGAs can be a pain. Even doing a simple hello world can be, a week's work for a developer, for an experienced RTL developer such as yourself. So, what chance does an average programmer have, right? So for this, no? It's less for you guys? Okay. So, yeah, okay. Let's say it's a few days for you guys. So we would like to make, obviously, this has to really take off. It has to be as easily programmable as possible, and less reliant on Verilog and VHDL. So the approach we have taken so far is to look at OpenCL being the mechanism. I'll come to the OpenCL flow in a bit, but this is what the programming interface looks like. As you can see, you have the host application which is running on the CPU, and you have the AFU, accelerator functional unit, which is running on the FPGA, and you can offload some of the kernels from the host to the AFU through OpenCL. We'll see that flow, which was actually over there. So, as probably most of you are aware of the OpenCL flow, you have a host side interface and you have device side interface. You basically create a kernel, include that kernel on the device, and it spawns off multiple threads or hardware threads, or it creates a data path according to the kernel and basically does the execution. So you essentially have two EXEs, and then you have one that runs on the host and one that runs on the device. So this is what it looks like with Altera OpenCL compiler as well. It's just a standard sort of thing. So on the device side, on the host side, you basically have the enqueue write buffer, which basically takes all the kernels, writes them, and dispatches them onto the device, and then you implement the device kernel over here. And basically what it does is that for every work range, for every work item, it spawns a new thread or creates a data path and operates on that in a SIMD fashion. The Altera flow, what it does is actually takes the OpenCL and takes the OpenCL compiler, converts that into LLVM, and the Quartus system then sort of optimizes the, not actually Quartus, so the compiler itself actually optimizes the IR, then using Quartus generates the Verilog, and then dispatches that on the FPGA itself. So ultimately the intermediate representation is the LLVM IR, which is optimized. Some basic optimizations specific to the FPGA are done, and then the Verilog for that is generated. So this is how it looks like for a simple data parallel function, so the thing is, OpenCL is not actually built for an abstract machine, and that actually is not even abstract. It's a GPU. It's not an FPGA. So what Altera have done is that they have done some vendor extensions on the OpenCL library to make it more amenable to FPGA. So they do all sorts of implementations, so optimizations, etc., at the LLVM level or even at the Verilog level. but there are other approaches for this. We all know about Chisel, Krista's work. There's also a work ongoing at Stanford and at EPFL, and Nitin is here with us. Hopefully he will give a lightning talk about the DSL-based approach. So how you can create a family of DSLs based on your particular workload that you have in mind, turn it through the DSL compiler, and that DSL compiler can do application level optimizations. It can reuse parallel patterns and then write it on a particular backend device, which can be anything from multi-core to an FPGA or a GPU. So Nitin will give that lightning talk, explain his work. So I'll quickly go through some applications for which FPGAs are good. We all know about data compression and search, but the most important one are those which are actually, which are not that straightforward. And deep learning, I'm not sure how many of you are aware of deep learning? All of you? So deep learning is now the new big data, right? Everyone seems to be doing deep learning these days. So Facebook is known. So the face tagging on Facebook happens via deep learning, apparently. So it has. There are various deep learning neural networks. The key one is the CNN, convolutional neural network, and this was the work that was done by Microsoft. Actually, sorry, this is the work by Badu, if I'm not mistaken. Yeah, I think this is Badu. So Badu, the Chinese Google, they implemented this algorithm on a Xeon FPGA and basically speeded up the convolutional neural network by 2.2x times. The important thing is on LXNet, I don't think I have a slide. I will see if I have a slide for this. The GPUs still outperform, but if you look at the images per second per watt, then FPGA is actually much better. If you want more details, look at Eric Chung's talk in ISCA this year. So he went over that. Oh, actually, I have that. So, yeah. So this is the Microsoft search example that they did with Bing. This got a lot of press recently, and this was basically like a page rank algorithm, right? It's not something that you associate with FPGAs and so on, and they were able to get some impressive sort of numbers from it. The one example that I'm looking at is genomics analysis. This is going to be a very interesting use case, especially for cancer treatments and so on. So this is the GATK, which is at the Broad Institute in MIT. And what basically it does is that it tries to do genome-wide association studies and variant calling. So all of us, we have our DNA, which is 99.9% same, but the 0.1 or 0.01% is responsible for our differences in phenotype, and also responsible for the various diseases that we can have, for example, cancer. So it's important that we track these mutations, as it were, and have a path through which we can, search the mutations and also look at certain chemical, proteins which can address that mutation and hopefully reverse a particular cancer, or at least remedy it to some extent. The aim is to do this. So Intel has taken an action. It's called All in a Day. So currently, this full flow from the sequence to the variant, and I'm not even talking about the treatment regime. It takes to the order of months, which can be a case of life and death. Our goal is to shrink it to a day, barring, of course, there are other human factors. So doctors have to. So at least the computational side, we want to shrink it to a day. So that's the pipeline that we are working on in terms of optimizing this whole variant calling sort of pipeline for genomics. And we took a kernel that is quite used for this variant calling phase. It's called pair HMM, hidden Markov model, and we implemented it on a FPGA device and got a 3.8x performance. Keep in mind that this is a PCIe attached FPGA. With a coherent FPGA, we anticipate 2x at least, so 7x. Sorry?
That's what you implemented it in. What language you used to implement FPGA?
Oh yeah, so GATK is implemented in Java, so we took the PHMM kernel and rewrote that in OpenCL. So that optimized it.
Sorry, now we have a couple of minutes left, I think.
Yeah, I'll just quickly finish it now. So database query processing is another one, but I won't go into this. FPGA I/O data streaming is another one. Open vSwitch is also very interesting. So those of you who follow SDN probably know about Open vSwitch. So what we are looking into is doing the packet processing. So the control plane is still going to be the Xeon, but the packet processing will be done on the FPGA by using the DPDK library. So things like header matching, flow matching, all that sort of stuff can be offered to the FPGA. The ultimate goal is to really create a programmer-friendly acceleration, and OpenCL 2.0 will probably have some sort of new shared version memory pipes, some new abstractions which will make it more programmer-friendly. But this is something that we are working on. So our ultimate goal is to have a consistent programming model for all accelerators. And so this is the same slide I told you earlier, like library instructions and so on, and achieve this area. Now, the important part for which I gave stock actually is in the last slide. So what does it mean for you guys, right? So ultimately what we'd like to do is achieve scale, and especially in a cloud environment, and you achieve scale these days by deploying a solution in a cloud environment. Ultimately, we would like to have this, this is a Xeon FPGA, so it will probably get deployed in the data center. What we'd like to see is the potential to have the FPGA bit stream orchestrated in a virtualized environment, so that you can actually have a cloud computing solution which has the standard Xeon part, but also has a customized FPGA part. So think of it like an iTunes-like model of IPs, an app store, if you like, of IP, which we can actually deploy on the. So if there's, for example, new deep learning algorithm that you have implemented, and that needs to be, that can be an IP that can go on the FPGA itself, and the orchestration piece, which is OpenStack, can take care of that and deploy that cloud accordingly. Obviously, acceleration will go beyond the CPU, and Intel is working on various technologies, which you will see in a few years, which together with the FPGA platform will create really what we envisage is going to take us to exascale. I believe in exascale. So summary and next steps, we think that Xeon FPGA is going to create a fundamentally new platform and unlock some workloads which are not possible at the moment. The big debate is really what the programming model will look like. In this conference alone, I think yesterday alone, I heard some 5-6 different frameworks, which is good. But obviously we need some sort of industry-backed standards, best known methods, a community, and this is where I think you guys come in, and I think this is where I think we can probably work together with other players as well to develop that traction. And the HARP is the prototype that I showed you in that slide. That's available to certain academic institutions. I think Vista has one, EPFL has another, CERN has another. So there will be another call for HARP. So if you guys are interested, let me know. So acknowledgements for PK Gupta and Microsoft Research team. Thank you so much for your attention. Thank you.
Is the QPI interface soft IP or hard IP?
So right now it's soft IP, so it's implemented like that. But eventually it will probably. No, not probably there won't be. Yeah,
That's tricky then.
yeah.
Good question.
Yeah, I'm very interested in what you call that App Store model. What will you use as, what standard will you be using to package the cores?
That's all up for discussion. So at the moment, I believe it's use the standard alternative stream protocol. There is a way to encrypt your bitstream as well. But but yeah, that is up for discussion right now because it will rely on what the FPGA supports and so on. But yeah, right now it's the standard distinct transistor.
Yeah. Normally, when Intel releases something like a, say, new packed SIMD extension, then there is extensive documentation that comes with that, so that everyone can build their own compilers and things. Will there be something similar for this FPGA accelerator?
Well, that's the logic, right? So, so the thing is, the accelerator function unit that I was showing, ultimately, you know, as someone said, it is an ecosystem play, it's a mass market play. So Intel alone cannot, you know, we only have X number of engineers, you know, who cannot all the time be working on AFUs. So ultimately, to achieve that mass market, it has to be opened up so that standard interfaces are there for bitstream manipulation for security, trusted execution of bitstream. If, you know, if that bitstream gets corrupted and a malware gets injected, then how can? So there are ways that we can prevent these kinds of things happening through TPM and so on. All that is work under progress, but eventually that is the end game, as you mentioned, to reach that stage where it's an open platform. We want to make it an open platform like the way Xeon is at the moment. Otherwise, this will not succeed.
A short second question.
Yeah.
Are there, or what are the plans to make this multi-user usable? I remember with GPUs this was a long process.
By multi-user,
so that that it's always possible that simultaneous processes can have their accelerations running without disturbing the accelerations of other users,
yeah.
And also, of course, the security considerations.
Yeah, yeah, so that's a good question, and that will probably take some time. So, short answer is dynamic reconfiguration. So that's what we are looking at. So the FPGA can be sort of partitioned, if you like, into coarse-grained arrays. And so, for example, if I'm a user, I'm submitting work, I select a particular AFU to execute, and let's say immediately after you come in and you want your own AFU. So the plan is that it should be the base, the IP that manages all these different AFUs will remain on the FPGA, but it can be dynamically reconfigured so that your AFU can be loaded simultaneously as other persons. So this is achieved through dynamic reconfiguration, and there's a plan to make that happen using coarse-grained arrays as well within the FPGA fabric.
We're going to have to leave it there, guys. We're over time massively. Thank you very much, Gaurav.